Close your eyes for a moment and picture this: an entire universe teeming with mysteries our eyes can't see. Galaxies hiding in plain sight, vast clouds of invisible matter weaving through the cosmos, and cosmic secrets lurking just beyond the limits of our vision. Now imagine if we had a way to peel back that veil, to uncover the invisible architecture of the universe itself. What if I told you we already do? Thanks to a phenomenon called gravitational lensing, scientists are turning the fabric of spacetime into a cosmic magnifying glass, revealing wonders we once thought were forever out of reach. This isn't science fiction, it's happening right now. Gravitational lensing, one of Einstein's most mind-bending predictions, occurs when massive objects like galaxies or black holes warp the space around them so profoundly that they bend light itself. Think of it like looking through a glass of water and watching the world behind it twist and stretch. Only here, the glass is the gravity of a galaxy, and the twisted image behind it could be a hidden universe, galaxies too faint or distant for our telescopes to spot, or even the ghostly fingerprints of dark matter, the mysterious substance that makes up most of our cosmos. What makes this so extraordinary isn't just the science, it's what it means for us. For the first time in history, we're not just guessing about the invisible forces shaping the universe. We're seeing them. Gravitational lensing is giving us front-row seats to the greatest show in existence, uncovering hidden galaxies, mapping dark matter, and even offering clues about the fate of the cosmos itself. And this is just the beginning. Today, we're diving deep into how this futuristic technology works, the breathtaking discoveries it's already unlocked, and the mind-blowing possibilities it holds for the future. From unraveling the mysteries of black holes to peering back to the very dawn of time. Buckle up, because we're about to explore the universe in a way you've never seen before. Einstein's theory of general relativity flipped our understanding of gravity upside down. Instead of thinking of it as just a force pulling objects together, he revealed that gravity is actually the curvature of spacetime itself, like placing a heavy object on a stretched-out bedsheet. Picture a bowling ball sitting in the center of a trampoline. The weight of the ball creates a deep dip in the fabric, and if you roll a marble nearby, it spirals inward following the curve. Now replace the trampoline with the fabric of the universe, and the bowling ball with a massive object like a galaxy or black hole. That dip in space-time doesn't just affect objects moving through it, it bends light itself, warping the path of photons as they travel across the cosmos. This is the essence of gravitational lensing. When light from a distant star or galaxy passes near a massive object, its path gets deflected, much like how a glass lens bends light to focus it. Sometimes this distortion creates multiple images of the same object, smeared into arcs or even complete rings, like looking at a street lamp through the bottom of a wine glass. Other times, it acts like a natural telescope, magnifying faint galaxies so far away they'd otherwise be invisible to us. The heavier the object, the stronger the lensing effect. A single galaxy can bend light from objects directly behind it, while enormous galaxy clusters, cosmic heavyweights, can twist entire patches of sky into funhouse mirrors, revealing dozens of stretched and warped background galaxies in a single snapshot. What's wild is that this isn't just theoretical. Astronomers first confirmed gravitational lensing during a solar eclipse in 1919, when they saw starlight bending around the sun exactly as Einstein predicted. Today, we've moved far beyond that proof of concept. With tools like the Hubble Space Telescope and now the James Webb Space Telescope, we're using gravitational lensing to probe the darkest corners of the universe. It's like nature handed us a cheat code. By studying how light bends around galaxies and clusters, we can map the distribution of matter we can't see, including the elusive dark matter that makes up most of the universe's mass. And here's where it gets even more mind-blowing. Because light takes time to travel, lensing doesn't just show us distant objects, it lets us see them at different points in their history. A single-lensed galaxy might appear multiple times in one image, each version showing it at a slightly different age, like flipping through pages of a cosmic photo album. This isn't just bending light, it's bending time, giving us a glimpse into the universe's past that no ordinary telescope could ever capture. The universe doesn't reveal its secrets in just one way. Gravitational lensing comes in 3 distinct flavors, each with its own cosmic superpower. First up, strong lensing, the showstopper of the trio. When a massive object like a galaxy cluster sits perfectly between us and a distant galaxy, it doesn't just bend the light, it warps it into mind-bending arcs, rings, or even multiple mirrored images of the same object. Picture a cosmic magnifying glass so powerful it turns a single galaxy into a smeared halo or a dazzling Einstein ring, a perfect circle of light named, of course, after the man who predicted it. These dramatic distortions aren't just beautiful, they're treasure maps. By studying these arcs, astronomers can calculate the mass of the lensing galaxy or cluster, including the invisible dark matter that makes up most of its weight. It's like weighing an object by watching how it bends the air around it, except here, the air is spacetime itself. Then there's weak lensing, the universe's subtle whisper. Instead of jaw-dropping arcs, weak lensing gently stretches the shapes of background galaxies, like a fingerprint pressed into cosmic light. The effect is so slight you'd never notice it by eye. It takes statistical analysis of thousands of galaxies to detect their collective squish or stretch. But don't let its understated nature fool you. Weak lensing is one of our most powerful tools for mapping dark matter on the largest scales. Imagine painting a portrait of the cosmos not with bold strokes, but with countless tiny brushstrokes, each revealing how unseen matter tugs at the fabric of space. Surveys like the Dark Energy Camera and future missions like the Vera Rubin Observatory rely on weak lensing to trace the invisible scaffolding of the universe, helping us understand how dark matter shapes galaxies and how dark energy drives the cosmos apart. Finally, there's microlensing, the cosmic zoom lens for individual stars. Here, a smaller object like a rogue planet, a neutron star, or even a black hole passes in front of a distant star, briefly amplifying its light like a natural spotlight. Unlike strong or weak lensing, microlensing doesn't distort shapes, it creates temporary brightening, a flicker in the darkness that can last hours, days, or months before fading away. This flicker holds clues to objects we'd otherwise never spot. Rogue planets drifting between stars, black holes lurking undetected, or even exotic objects like quark stars. Microlensing is also our best hope for finding Earth-like planets in the galactic wilderness, especially those floating far from any star's warmth. By monitoring millions of stars, projects like the Optical Gravitational Lensing Experiment have discovered worlds that defy textbook definitions, planets orphaned from their suns, or so distant they're barely warmed by their star's glow. What's astonishing is how these 3 techniques complement each other. Strong lensing shows us the universe's most dramatic distortions, weak lensing reveals its hidden architecture, and microlensing spots the cosmic loners, objects too faint or isolated for other methods. Together, they're like a toolkit for decoding the invisible, turning gravity's tricks into a way to see the unseeable. Whether it's mapping dark matter, spotting orphan planets, or glimpsing galaxies at the edge of time, gravitational lensing isn't just a window into the cosmos, it's a whole new way of seeing. Before the Hubble Space Telescope launched, gravitational lensing was more theory than reality, something astronomers knew should exist but struggled to observe with Earth's blurry atmosphere in the way. Then Hubble changed everything. Floating above the distortions of our planet with its razor-sharp vision, it didn't just spot lensed galaxies, it turned them into cosmic landmarks. One of its most stunning finds, the Einstein Cross, a perfect example of nature's optical illusion. Here, a distant quasar's light gets split into 4 glowing points around a foreground galaxy, like a celestial diamond ring. This wasn't just a pretty picture, it was proof that Einstein's wildest ideas could play out on scales even he might not have imagined. But Hubble's greatest gift was how it transformed lensing from a curiosity into a tool. By capturing galaxy clusters like Abell 1689 with unprecedented clarity, Hubble revealed how their gravity twisted the light of hundreds of background galaxies into delicate arcs, a spiderweb of warped spacetime. Scientists realized these distortions weren't random, they were clues. By mapping the arcs, they could weigh the clusters themselves, including the invisible dark matter holding them together. It was like discovering an X-ray machine for the cosmos, exposing the skeleton beneath the universe's skin. And then there were the deep fields Hubble's marathon stares into seemingly empty patches of sky. Peering through gravitational lenses, it spotted galaxies so young and faint they existed just a few 100 million years after the Big Bang. Without lensing, these ancient objects would have been lost in the glare of time. But with nature's magnification, Hubble gave us baby pictures of the universe, showing how early galaxies grew and evolved. The real magic, Hubble didn't just observe lensing, it taught us how to use it. Every warped image, every stretched galaxy became a data point in a grander puzzle. How dark matter clumps, how galaxies form, even how fast the universe expands. It turned what could have been cosmic quirks into a universal measuring tape. And when Hubble's successor, the James Webb Space Telescope, launched, it built on that legacy, using lensing to push even further back in time. Together, they've shown us that sometimes, to see the universe clearly, you first need to embrace its bends and twists. Of all the cosmic mysteries gravitational lensing has helped unravel, none is more profound than dark matter, the invisible glue holding our universe together. We can't see it, touch it, or detect it directly, yet its gravitational pull shapes galaxies, bends light, and dictates the fate of the cosmos. How do you study something that refuses to interact with light? You follow the shadows it leaves on spacetime itself. Take the bullet cluster, one of the most compelling pieces of evidence for dark matter's existence. When 2 galaxy clusters collided at millions of kilometers per hour, their visible gas-hot and dense slammed together like cosmic bumper cars, glowing brightly in X-ray images. But something bizarre happened. By mapping the cluster's gravity using gravitational lensing, scientists found most of their mass wasn't where the gas was. Instead, it lurked in 2 ghostly blobs on either side, untouched by the collision. That missing mass, dark matter, sailing through the wreckage unaffected because, unlike normal matter, it doesn't collide or emit light. The bullet cluster wasn't just a cosmic accident, it was a smoking gun, proving dark matter isn't a placeholder in equations but a real, physical substance shaping the universe. But lensing does more than confirm dark matter exists, it lets us trace its hidden architecture. When light from distant galaxies passes through a cluster, the way it bends reveals the cluster's total mass, including the invisible dark matter woven through it. The result, maps of cosmic scaffolding, showing dark matter as a vast, intricate web stretching across the universe. Some of these maps have uncovered surprises, like galaxies with almost no dark matter, defying theories of how galaxies form, or strands of dark matter connecting clusters like invisible bridges. Perhaps the most mind-bending discovery is how dark matter's distribution aligns with Einstein's predictions. In some clusters, lensing reveals dark matter piled up exactly where his equations said it should be, even when visible matter is scattered elsewhere. It's as if the universe left us a trail of breadcrumbs in gravity's language, and lensing gave us the key to read them. What's next? Projects like the Euclid Space Telescope are turning lensing into a dark matter census, scanning billions of galaxies to map its influence across cosmic time. With every warped image, every stretched galaxy, we're peeling back the veil on the universe's greatest mystery, not by seeing dark matter, but by seeing through it. Among all the wonders gravitational lensing creates, few are as mesmerizing or as exacting as Einstein Rings. Picture this, a perfect halo of light encircling a galaxy like a cosmic bullseye, so precise it seems sculpted by an unseen hand. These rare and breathtaking formations are nature's way of showing us just how perfectly Einstein's equations map onto reality. When a distant galaxy, a massive foreground object like another galaxy, and our viewpoint on Earth align with flawless precision, the background galaxy's light gets bent into a complete circle around the foreground mass. It's as if the universe itself handed us a geometry problem and then solved it in starlight. What makes Einstein Rings so extraordinary isn't just their beauty, it's their precision. The diameter of the ring isn't random, it's a direct measure of the foreground object's mass and the alignment's perfection. A tiny shift in any direction would break the symmetry, turning the ring into arcs or multiple images. That's why spotting one feels like finding a cosmic needle in a haystack. The first confirmed Einstein ring, discovered in 1998 and nicknamed the Cosmic Horseshoe, stretched nearly 300 degrees around its lensing galaxy, a near-perfect circle that left astronomers in awe. Since then, fewer than a dozen pristine rings have been found, each one a time capsule of mathematical elegance written in gravity's handwriting. But these rings aren't just celestial eye candy, they're laboratories for testing the universe's deepest rules. By studying their structure, scientists can measure the mass of the lensing galaxy down to the last star and dust particle, including the dark matter halo shrouding it. Some rings even reveal knots of brightness along their edges, multiple images of the same star-forming regions in the background galaxy, magnified and mirrored by the lens. It's like getting a magnified 3D view of a galaxy we'd otherwise never resolve, all thanks to spacetime's curvature. One of the most stunning examples, the molten ring, spotted by the Hubble Space Telescope in 2020, shows a distant galaxy stretched into a near-flawless golden loop. But here's the twist. The ring isn't just a circle, it's slightly warped, a subtle clue that the lensing galaxy isn't perfectly spherical. That tiny imperfection tells a story about how dark matter is distributed within it, offering a window into the invisible skeleton shaping the cosmos. And sometimes Einstein rings surprise us entirely. Take the case of SPT 2031, where astronomers found not one but two rings stacked around the same foreground galaxy, created by light from two different background galaxies at varying distances. It's a cosmic matryoshka doll, with each ring encoding information about a different epoch in the universe's history. What's truly humbling is that these rings are more than just rare alignments. They're proof that the universe plays by rules we can decipher. Every perfect circle, every warped arc is a reminder that even in the vast chaos of space, there's an underlying order waiting to be read, if only we know how to look. Galaxy clusters are nature's ultimate telescope's cosmic behemoths, so massive they don't just bend light, they amplify it. Take Able 1689, a sprawling metropolis of galaxies over 2 billion light-years away. To the naked eye, it's a smudge of faint stars, but through the lens of gravity, it becomes a portal to the universe's furthest edges. The cluster's immense gravity, a mix of hundreds of galaxies and an ocean of dark matter, warps spacetime so dramatically that light from galaxies behind it gets stretched, brightened, and twisted into vivid arcs. These aren't just distortions, they're lifelines to realms we'd otherwise never glimpse. Without this natural magnification, many of these background galaxies would be lost in the cosmic static, too dim for even our most powerful telescopes to detect. But thanks to Able 1689's gravitational heft, their light gets a free boost, like a whisper turned into a shout. Some of these lensed galaxies are so far away we're seeing them as they were just a few 100 million years after the Big Bang, infant galaxies caught in their first moments of star formation. It's as if the cluster handed us a time machine, compressing billions of years into a single frame. One of Hubble's most iconic images of Able 1689 reveals over 100 stretched and smeared galaxies, each one a puzzle piece in understanding the early universe. Among them, a galaxy nicknamed the Cosmic Eyebrow appears as a delicate arc magnified 30 times its normal brightness. Without the cluster's intervention, it would have been a faint blip, invisible against the blackness of space. Instead, we can study its newborn stars, its chemical makeup, even the seeds of its spiral arms, details we'd have no hope of seeing otherwise. But the real magic lies in the unexpected. When scientists mapped the cluster's mass using these lensed galaxies, they found surprises: patches of dark matter clumping in ways models didn't predict, or galaxies so ancient they challenge our theories of cosmic evolution. Every warped image is a breadcrumb leading us deeper into the unknown, and with tools like the James Webb Space Telescope now peering through these natural lenses, we're spotting galaxies so primordial they lack heavy metals entirely, forged from nothing but the universe's rawest ingredients. What's revolutionary is how this transforms our approach to exploration. Instead of building bigger telescopes on Earth, we're learning to harness gravity's own optics, turning galaxy clusters into colossal observatories. Future missions plan to target even more massive clusters, using their distorting power to hunt for the universe's first galaxies, or even elusive population 3 stars. The hypothetical pure hydrogen giants thought to have lit up the cosmos before metals existed. It's a reminder that sometimes the universe itself provides the best tools for its own discovery. Here's a quirk of gravitational lensing that sounds like science fiction. Sometimes you can watch the same cosmic event unfold multiple times. Not just from different angles, but days, weeks, or even years apart. This bizarre effect, called time delay lensing, happens when light from a distant object like a quasar takes multiple paths around a massive foreground galaxy. Some paths are shorter, others loop around the galaxy's gravitational well, adding extra miles, or rather extra light years, to the journey. The result: light that left the quasar at the same moment arrives at Earth at different times, like staggered echoes of the same shout. But here's where it gets revolutionary. By measuring these delays, precisely timing how long it takes for each version of the quasar's light to reach us, astronomers can calculate the distance to the quasar and the lensing galaxy with extraordinary accuracy. Why does that matter? Because these measurements hold the key to one of cosmology's biggest fights: how fast the universe is expanding. The expansion rate, known as Hubble's constant, should be a straightforward number. Yet for years, 2 methods of measuring it have produced stubbornly different results. One approach, using the cosmic microwave background, suggests a slower expansion. The other, based on nearby supernova, insists it's faster. The discrepancy has physicists questioning whether we've overlooked something fundamental: a hidden ingredient in the universe, or even a flaw in our understanding of gravity itself. Time delay lensing offers a third way to settle the debate. In 2017, the Hubble Space Telescope measured delays in a lensed quasar called JWST 095 plus 2568, clocking the staggered arrivals of its light to within a razor-thin margin of error. The result: an expansion rate smack in the middle of the other 2 methods, deepening the mystery instead of solving it. But newer observations, like those from the H0 lenses in Cosmogral Wellspring program, are refining the technique further. By tracking quasars that flicker predictably, their bright cores pulsing like cosmic lighthouses, scientists can measure delays down to mere hours, turning each lensed image into a stopwatch for the universe's expansion. What's thrilling is how this transforms a cosmic oddity into a precision tool. Every lensed quasar becomes a laboratory for testing gravity's grip on spacetime, or for hunting phantom forces like dark energy. Some theories suggest the expansion rate might change over cosmic distances, a wrinkle that could explain the conflicting measurements. Time delay lensing lets us test that idea directly, comparing delays in nearby lenses to those billions of light years away. It's as if the universe handed us a ruler with one end anchored in the present and the other reaching back to its infancy, and we're just learning how to read the markings. The stakes couldn't be higher. If the discrepancy in Hubble's constant persists, it might mean our universe isn't just expanding, it's doing so in ways we can't yet explain. Maybe dark energy isn't constant after all, or perhaps gravity behaves differently on cosmic scales. Time delay lensing doesn't just measure the universe's growth, it challenges us to rethink how that growth works. And with next-generation telescopes like the Vera Rubin Observatory set to discover thousands more lensed quasars, we're on the verge of turning this cosmic quirk into a golden age of discovery, one delayed photon at a time. Gravitational microlensing might sound like an obscure cosmic trick, but it's revolutionizing how we hunt for planets beyond our solar system, especially the ones traditional methods can't find. While techniques like the transit method, which watches for a star's dimming as a planet passes in front or radial velocity, detecting a star's wobble from an orbiting planet's pull rely on specific alignments or proximity, microlensing doesn't play by those rules. Instead, it exploits a simple yet profound fact: gravity doesn't care if a planet orbits a star or drifts alone in the void. Here's how it works. When a rogue planet or a distant star's planetary system passes in front of a background star, its gravity acts like a temporary lens, warping spacetime just enough to amplify the background star's light. For hours, days, or even weeks, that star brightens in a predictable curve, a telltale spike in brightness that reveals the lensing object's mass. If the object has planets, their gravity adds tiny bumps or dips to that curve, like fingerprints left on the light. The beauty: this method doesn't require the planet to be close to its star or even to have a star. It catches worlds orbiting at vast distances or none at all. Some of the most fascinating discoveries come from these cosmic nomads, rogue planets untethered from any star, wandering the galaxy in perpetual night. In 2018, microlensing revealed a potential rogue planet roughly the mass of Earth, floating freely in interstellar space. Without a sun to warm it, this world would be a frozen wasteland, but its very existence challenges our ideas of how planets form. Were they ejected from young solar systems, or did they coalesce from cold, isolated gas clouds like failed stars? Microlensing doesn't just find these outliers, it forces us to rethink what a planet even is. And then there are the exceptions that defy expectations. Take Ogle 2013 BLG 0341, a microlensing event that initially looked like a simple star-star alignment until the light curve revealed a bizarre anomaly. The culprit, a planet 2.5 times as far from its star as Pluto is from ours, yet somehow surviving in a region where theorists thought planetary formation was impossible. Microlensing doesn't just add to the exoplanet catalog, it fills in the margins with worlds that shouldn't exist, rewriting the rules as it goes. What makes this technique so powerful is its reach. While other methods favor planets close to bright, nearby stars, microlensing peers deep into the galactic bulge where stars and their planets are packed like sardines. Projects like the Optical Gravitational Lensing Experiment scan millions of stars nightly, catching these fleeting cosmic alignments. One of its landmark finds, Ogle 2015 BLG 0966, uncovered a rocky planet just 1.5 times Earth's mass orbiting a dim red dwarf, a whisper of a world that transit surveys might have missed entirely. But microlensing has its quirks. Unlike transits which repeat predictably, each lensing event is a one-time show. Once the alignment passes, it's gone forever. That means every detection is a race against time, with astronomers scrambling to confirm findings before the light fades. And because the method relies on chance alignments, it's inherently rare, like spotting a firefly flicker once in a lifetime. Yet despite these challenges, microlensing has unveiled thousands of exoplanet candidates, including some of the coldest, most distant worlds ever recorded. The future is even brighter. NASA's upcoming Nancy Grace Roman Space Telescope, set to launch in the mid-2000s, will turn microlensing into a high-precision sensors, scanning the galaxy for planets down to Mars's size, even those floating between the stars. Combined with ground-based surveys, it could reveal whether rogue planets outnumber stars, or if every star in the sky hosts planets too distant and dim for other methods to catch. In the end, microlensing isn't just a tool for planet hunting. It's a reminder that the universe hides its most intriguing secrets in the gaps, the outliers, and the seemingly impossible. By bending light, these unseen worlds bend our imagination, proving that the cosmic neighborhood is far stranger and far richer than we ever dreamed. Imagine trying to find a single bent straw in a haystack the size of a galaxy. That's the challenge astronomers face when hunting for gravitational lenses in the flood of data from modern telescopes. Every night, observatories like the Vera Rubin scan vast swaths of sky, capturing billions of cosmic objects in unprecedented detail. Hidden among them are the telltale arcs, rings, and distortions of lensing events, but spotting them manually would take lifetimes. That's where artificial intelligence steps in, transforming what was once a painstaking human task into a high-speed cosmic treasure hunt. These AI systems don't just scan data, they learn from it. Trained on thousands of confirmed lensing images, machine learning algorithms can now recognize the subtle signatures of warped spacetime with superhuman precision. Take the groundbreaking work of projects like Google's DeepMind and the Space Warp's Citizen Science Initiative. Their neural networks analyze telescope images pixel by pixel, flagging distortions that even seasoned astronomers might miss. Some algorithms go further, simulating how hypothetical lenses should look and comparing them to real data, a digital version of holding up a cosmic fingerprint to the light. The real breakthrough: speed. In 2021, an AI sifted through 40,000 galaxy clusters in days, identifying potential lenses that would have taken humans years to catalog. But these tools aren't just fast, they're creative. One algorithm recently discovered a new class of ultra-faint lenses by detecting patterns no human had thought to look for, slight asymmetries in galaxy shapes that hinted at invisible dark matter's tug. It's like teaching a computer to read the universe's invisible ink, and the stakes keep rising. With the James Webb Space Telescope beaming back terabytes of high-resolution images, AI has become astronomy's essential collaborator. Some systems now combine lens finding with real-time physics simulations, calculating a lens's mass distribution while analyzing its image, a feat akin to diagnosing a patient's entire medical history from a single X-ray. Others, like the European Space Agency's Euclid mission, use machine learning to prioritize which lenses warrant follow-up study, turning chaotic data streams into targeted discovery pipelines. Yet for all their prowess, these algorithms still need human partners. When an AI spotted a bizarre, cross-shaped lens in 2022, it took astrophysicists months to realize they'd found something even rarer. Two massive galaxies aligned so precisely they created a gravitational lens within another lens, a cosmic Russian nesting doll. It's a reminder that in this partnership, machines handle the scale, but humans bring the wonder. Together, they're rewriting the playbook for cosmic exploration, one pixel at a time. The James Webb Space Telescope isn't just another observatory, it's a time machine with infrared vision, built to peer through the cosmic fog that's hidden the universe's earliest moments from view. While Hubble gave us our first glimpse of lensed galaxies, JWST is taking that revelation to staggering new depths. Imagine trying to read a letter through a dusty window. Hubble wiped away some of the grime, but JWST is tearing the window clean off, revealing words written in starlight over 13 billion years ago. This revolution starts with wavelength. Unlike Hubble, which primarily observes visible and ultraviolet light, JWST infrared eyes cut through the obscuring dust and gas that shroud newborn galaxies. But combine that with gravitational lensing and something extraordinary happens. Massive galaxy clusters acting as natural telescopes amplify the faint infrared glow from the universe's first galaxy's light that's been stretched into longer, redder wavelengths by cosmic expansion. It's like turning up the volume on whispers from the dawn of time. Already, JWST has shattered expectations. One of its earliest lensing targets, the galaxy cluster SMACS 0723, revealed hundreds of background galaxies warped into luminous arcs, some dating back to just 300 million years after the Big Bang. That's a cosmic toddler learning to walk, but here's the twist. Many of these infant galaxies are brighter, more massive, and more structured than models predicted. Some show fully formed disks and spiral arms, as if the universe figured out galaxy design far quicker than we thought. The implications are rewriting cosmic history. If galaxies matured this fast, it could mean star formation in the early universe was a frenzied, hyper-efficient process, or that dark matter played a more active role in shaping galaxies than we realized. JWST lensed snapshots aren't just pretty pictures, they're forensic evidence challenging our timelines for when stars first ignited, when metals first seeded space, even when the cosmic, dark ages ended. But the real magic lies in the details. Spectra from these lensed galaxies, their light split into rainbows by JWST instruments, reveal chemical fingerprints. Some show unexpected oxygen levels, suggesting stars lived, died, and recycled their material into new generations at breakneck speeds. Others lack heavy elements entirely, offering glimpses of primordial stars so massive and hot they defy modern astrophysics. These aren't just ancient objects, they're relics of a universe operating under different rules, and the discoveries keep accelerating. JWST's latest lensing surveys have uncovered candidate galaxies so early in cosmic history that their existence teeters on the edge of impossibility, pushing the era of galaxy formation perilously close to the Big Bang itself. Each one forces us to ask, did galaxies form in sudden bursts, or is our understanding of cosmic inflation flawed? Could dark matter have clumped faster than simulations suggest? The answers are hidden in those magnified wisps of infrared light. What's next? JWST is turning lensing into a precision tool for the early universe. By targeting clusters like El Gordo and the Pandora cluster, it's assembling a lensed mosaic of the cosmos's first chapters, one where every warped galaxy is a sentence in a story we're just learning to read. Future observations aim to catch population 3 stars, the mythical first stars made purely of hydrogen and helium, whose lensed signatures might flicker like cosmic fireflies in the dark. The telescope's greatest gift isn't just seeing farther, it's seeing differently. By marrying gravitational lensing with infrared brilliance, JWST isn't just observing history, it's forcing us to rewrite it. Every smudge of light in its lensed snapshots is a revolution waiting to happen, a clue that the universe's infancy was stranger, wilder, and more beautiful than we ever imagined. Gravitational lensing doesn't just reveal isolated galaxies or clusters, it exposes the universe's hidden architecture, the vast cosmic web threading through the emptiness like an invisible nervous system. Picture the universe not as scattered islands of matter, but as an interconnected network of dark matter filaments, stretching billions of light years and funneling galaxies into dense clusters at their intersections. This web, though invisible, leaves its fingerprints everywhere. When light from distant quasars or galaxies travels through these filaments, it doesn't pass through unimpeded. Instead, the collective gravity of these wispy dark matter tendrils bends the light ever so slightly, a phenomenon called weak lensing on a cosmic scale. These distortions are subtle, far less dramatic than the vivid arcs of strong lensing, but they are the key to mapping the universe's skeleton. Imagine holding up a sheer curtain and watching the pattern of streetlights behind it shift imperceptibly. By measuring how millions of background galaxies appear slightly stretched or aligned in the same direction, astronomers can reconstruct the distribution of dark matter between them. Projects like the Dark Energy Survey have used this technique to create 3D maps of the cosmic web, revealing how filaments weave through voids, forming a sponge-like structure where galaxies cling to the densest threads. One of the most astonishing revelations, the cosmic web isn't static. It's a dynamic, growing entity. Simulations show dark matter flowing along these filaments like rivers feeding into lakes, channeling galaxies toward the intersections where clusters form. Lensing confirms this motion. In 2018, researchers studying the galaxy cluster Abell 786 found dark matter streams flowing into the cluster, matching predictions of how the web funnels matter into gravitational wells. It's as if we're watching the universe's plumbing system in action, with dark matter as the water and gravity as the force pulling it downhill. But here's where it gets even stranger. The cosmic web doesn't just organize matter, it shapes the fate of galaxies. Galaxies nestled along dense filaments tend to grow faster, fed by a steady supply of gas funneled through these dark matter highways. Those stranded in voids cut off from the web often starve, becoming cosmic ghost towns with little new star formation. Lensing lets us see this hierarchy in action. By comparing lensing maps with galaxy surveys, astronomers have spotted filament galaxies spinning in alignment with the dark matter threads around them, as if the universe itself is whispering directions to their growth. Perhaps the most profound implication is what this tells us about dark energy, the mysterious force accelerating the universe's expansion. The cosmic web's structure holds clues to how dark energy battles gravity over cosmic time. As filaments stretch and thin, their lensing signatures change, offering a way to measure dark energy's grip on the universe's expansion. Future missions like the Euclid Space Telescope aim to use weak lensing to trace the web's evolution across 10 billion years, turning these faint distortions into a time-lapse of the universe's largest structure. What's humbling is realizing that gravitational lensing doesn't just show us objects, it reveals the scaffolding behind them. Every slight warp in a galaxy's shape, every stretched quasar image, is a breadcrumb leading us deeper into the dark universe's blueprint. And as our maps grow sharper, we're uncovering something startling. The cosmos isn't just expanding, it's breathing, pulsing, and growing according to rhythms written in the language of gravity and light, a story we're only beginning to decipher. For decades, gravitational waves and gravitational lensing have revolutionized our understanding of the cosmos, but separately. Now, imagine what happens when these two cosmic phenomena collide. A black hole merger, warping spacetime as it spirals toward catastrophe, while somewhere along its journey to Earth, its gravitational ripples pass through a massive galaxy cluster. That cluster bends and distorts the waves just like it bends light, stretching them, delaying them, even splitting them into multiple copies. Suddenly, we're not just detecting gravitational waves, we're seeing them through nature's own funhouse mirror, unlocking secrets about the universe we could never access before. This isn't science fiction, it's the next frontier. When gravitational waves get lensed, they don't just tell us about the objects that produced them, they reveal the invisible mass they encountered along the way. Picture two neutron stars colliding in a distant galaxy. Normally, the gravitational waves from such an event give us a snapshot, the masses of the stars, their spin, the energy released. But if those waves are lensed by a galaxy cluster on their way to us, the signal splits into multiple arrivals, each one taking a slightly different path through the universe's dark matter scaffolding. By analyzing the delays between these echoes, we could map the cluster's mass distribution with unprecedented precision, including the dark matter we can't see. It's like turning a black hole merger into a sonar pulse for the cosmos. The implications are staggering. Lensed gravitational waves could reveal the properties of merging black holes with freakish accuracy. For instance, if a lens splits the signal into two copies, the slight differences between them, like a fingerprint smudged by spacetime, could let us measure the black hole's spins and orientations far better than a single unlensed wave ever could. Even more tantalizing, some theories predict that certain exotic objects, like primordial black holes from the Big Bang or cosmic strings fractures in spacetime itself, could lens gravitational waves in unique ways, leaving signatures no other method could detect. But the real game changer is time. Gravitational wave events are fleeting, often lasting mere seconds, yet lensing can stretch our observation window, replaying the same merger hours, days, or even years apart as the lensed signals arrive at different times. Imagine catching the final moments of a black hole collision, then catching it again months later, this time with upgraded detectors or new telescopes trained on the event. It's like getting a second chance to study the universe's most violent explosions. Of course, the challenges are immense. Gravitational wave detectors like LIGO and Virgo aren't yet sensitive enough to routinely catch lensed signals, and distinguishing a true lensed wave from background noise is like picking out a whisper in a hurricane. But next-generation observatories like the Einstein telescope or the space-based LISA mission could change that. With their vastly improved sensitivity, they'll scan the cosmos for these warped ripples, turning rare anomalies into a new branch of astronomy. And the discoveries won't stop there. If we're lucky, lensed gravitational waves might even resolve one of cosmology's biggest headaches, the Hubble tension. Just as lensed light helps measure the universe's expansion rate, lensed gravitational waves could provide an independent check free from the uncertainties plaguing other methods. By comparing the arrival times of lensed echoes, we could pin down distances to merging black holes with razor-sharp accuracy, finally settling whether our universe is expanding faster than we thought. What's thrilling is how perfectly these two cosmic tricks complement each other. Lensing magnifies the faint and distant. Gravitational waves cut through the dust and gas that obscure light. Together, they could peer into regions of space-time no telescope can reach, like the chaotic edges of supermassive black holes or the hearts of neutron stars, where matter is crushed into bizarre states. The future isn't just about seeing the invisible universe, it's about hearing it too, in the warped echoes of space-time itself. And when those echoes start reaching us, they won't just answer old questions. They'll ask entirely new ones. Most black holes lurk in the darkness, their secrets locked behind an event horizon no light can escape. But quasars, supermassive black holes gorging on gas at the centers of galaxies, are different. These cosmic powerhouses blaze with radiation, their accretion disks glowing white-hot as matter spirals inward at nearly light speed. Normally, even the sharpest telescopes see them only as pinpricks of light, their details blurred across millions of light years. Yet, thanks to gravitational lensing, we're not just observing quasars, we're watching them change in real time, frame by frame. When a quasar's light gets lensed by a foreground galaxy, something remarkable happens. Stars within that galaxy can drift across our line of sight, their gravity acting like tiny magnifying glasses that amplify different parts of the quasar's accretion disk. This microlensing effect doesn't just brighten the quasar, it scans it, revealing regions we'd otherwise never resolve. Imagine shining a spotlight across a stage, illuminating one performer at a time. As the stars move, the spotlight shifts, exposing the quasar's inner structure piece by piece. The result, a flickering cosmic movie, with each frame unmasking a different slice of the black hole's violent neighborhood. One of the most breathtaking examples is the lensed quasar Q2237 plus 0305. Here, the quasar's light is split into 4 images by a foreground galaxy, each version flickering independently as stars pass in front. In 2014, astronomers noticed something extraordinary. One of these images began brightening rapidly while the others stayed steady, the culprit. A single star in the lensing galaxy had drifted into perfect alignment, magnifying a tiny patch of the quasar's accretion disk, a region no larger than our solar system, yet glowing with the energy of 1 trillion suns. For weeks, telescopes tracked this flare like a camera zooming in, revealing details about the disk's temperature, density, and even how it twists under the black hole's gravitational grip. But the real magic lies in the time delays, because each lensed quasar image takes a slightly different path around the galaxy. They arrive at Earth days or years apart. This means we can watch the same microlensing event play out multiple times, like catching a rerun of your favorite show, but with new clues hidden in each viewing. In 2021, researchers used this trick to map a quasar's disk in unprecedented detail. By comparing delayed versions of the same flicker, they reconstructed the disk's structure in 3D, confirming theories about how matter churns near the event horizon. What's even wilder is what these movies reveal about black hole physics. Some quasars flicker in ways that suggest their accretion disks aren't smooth plates of gas, but fractured into clumps or spiral arm structures that could explain mysterious bursts of X-rays or jets shooting from the poles. Others show shadows flickering across their disks, possibly from clouds of debris or even smaller black holes orbiting like sharks in a feeding frenzy. Each flicker is a breadcrumb leading us closer to understanding how black holes grow, how they launch jets that span galaxies, and how they shape the cosmos around them. The future holds even more promise. With observatories like the Vera Rubin scanning the sky nightly, we're on the verge of catching microlensing events as they start, training telescopes on quasars the moment they begin to flare. Combined with gravitational wave detectors, we might soon witness a supermassive black hole's disk ripple from an incoming stellar collision, a cosmic splash seen through two different lenses of spacetime itself. These aren't just snapshots of the universe's most extreme environments. They're live broadcasts from the edge of the unknown. Few scientific concepts have captured Hollywood's imagination like gravitational lensing. Whether bending starlight into impossible shapes or serving as a plot device for interstellar travel, lensing has become shorthand for cutting-edge astrophysics in blockbusters and sci-fi epics. But how much of what we see on screen holds up to reality? Let's start with the most iconic example, Interstellar. Christopher Nolan's visually stunning depiction of Gargantua, the supermassive black hole, was groundbreaking. Based on equations from physicist Kip Thorne, its glowing accretion disk and warped starlight were the first scientifically accurate renderings of lensing in film. The Einstein ring around Gargantua, real physics, the way nearby stars stretched into streaks, authentic. But here's where artistry took over. The film's lensing effects were amplified for drama. In reality, the distortions would be subtler, less like a funhouse mirror, and more like a faint ripple in space-time. Then there's Star Trek, where gravitational lensing often gets repurposed as a cosmic shortcut. Remember the slingshot effect, where ships use a star's gravity to time travel. While massive objects do bend light and slow time, the idea that a starship could harness lensing for precise time jumps leans heavily into creative liberty. Real lensing doesn't create portals or vortexes, it's a gradual curvature, not a trampoline. Yet Star Trek nails one subtle detail: the way lensing distorts views of planets or stars when ships approach at warp speed. Those shimmering, stretched visuals, a nod to real physics, even if the warp drive itself is pure fantasy. For sheer spectacle, Marvel's Doctor Strange takes the cake. The mirror dimensions kaleidoscopic cityscapes where buildings bend and fold like origami, borrow loosely from lensing's light-bending principles. But here, the science morphs into magic. Real gravitational lensing doesn't fracture space into infinite reflections. It's a predictable, if mind-bending, distortion governed by Einstein's equations. Still, the film's visual metaphor resonates because it taps into a deeper truth. Gravity does reshape our perception of reality. Where Hollywood often stumbles is scale. Films like Event Horizon or Contact depict lensing as instant dramatic warps, like flipping a switch. In reality, these effects unfold over cosmic distances and timescales. A lensed galaxy doesn't flicker like a neon sign. Its light might take centuries to reach us, stretched by gravity's patient hand. But in Arrival, the alien ship's haunting, lens-like silhouettes get closer to the eerie grandeur of real cosmic lenses, ominous yet precise, bending light without breaking the laws of physics. What's fascinating is how these portrayals shape public perception. When the Flash 2023 name drops gravitational lensing to explain time anomalies, it's not science, but it sparks curiosity. For every exaggerated warp effect, there's a viewer diving into NASA articles to learn the truth, and sometimes fiction anticipates reality. Babylon 5 gravitic telescopes used lensing to peer into distant star systems, a concept now mirrored by real astronomers using galaxy clusters as natural observatories. Perhaps the most poetic blend of art and science lies in Ad Astra, where lensing subtly distorts views of Neptune's rings, a quiet reminder of gravity's invisible hand. No flashy explosions, no time loops, just space bending light as it always has, beautiful in its understatement. That's the real magic of lensing, whether on screen or in a telescope. It reminds us that the universe's most profound truths are written in geometry, waiting to be read. You don't need a PhD or $1 million telescope to help uncover the secrets of gravitational lensing. Some of the most groundbreaking discoveries in this field have come from everyday people sitting at their kitchen tables, scrolling through telescope images online. Welcome to the world of citizen science, where anyone with curiosity and an internet connection can contribute to cutting-edge astronomy. Projects like Space Warp's Galaxy Zoo and the Hubble Asteroid Hunter have turned lensing into a global treasure hunt, inviting volunteers to spot the telltale arcs, rings, and warped galaxies hidden in vast datasets. Here's how it works. Telescopes like Hubble, the Subaru Telescope, and soon the Vera Rubin Observatory capture millions of high-resolution images of the sky, far more than professional astronomers could ever analyze alone. That's where you come in. Platforms like Zooniverse train volunteers to recognize the subtle distortions of lensing, guiding them through tutorials that explain what to look for. A smeared galaxy here, a stretched arc there, or maybe a rare Einstein ring tucked between the stars. The interface feels almost like a cosmic version of Where's Waldo, except instead of a striped shirt, you're hunting for spacetime itself, bending under the weight of invisible matter. And the results speak for themselves. In 2013, Space Warp's participants spotted dozens of previously unknown gravitational lenses in data from the Canada-France Hawaii telescope, some so unusual they made astronomers double-check their models. One volunteer, a retired teacher from Portugal, discovered a lensed quasar that had slipped past automated algorithms because its distortion was too faint. Another, a high school student in India, helped identify a galaxy cluster warping light so dramatically it became a priority target for the James Webb Space Telescope. These aren't just feel-good stories, they're proof that human intuition, especially our knack for spotting patterns, still outperforms machines when it comes to recognizing the universe's weirdest quirks. But the real magic lies in the collective effort. When thousands of volunteers independently flag the same odd-looking galaxy, astronomers can be confident it's worth a closer look. This wisdom of the crowd approach has even led to unexpected spin-off discoveries. During one Space Warp's campaign, participants noticed strange blue streaks that turned out to be the trails of asteroids photobombing distant galaxy images, data that's now helping track near-Earth objects. Other users have stumbled over galaxy mergers, supernova, and even mysterious green blobs that might be the remnants of ancient quasars. What's thrilling is how accessible it all is. You don't need fancy equipment or a background in astrophysics, just a willingness to learn and a few spare minutes. Some of the most prolific citizen scientists are retirees, teachers, or even kids scrolling on their phones. And with projects expanding into virtual reality and AI-assisted tagging, the next generation of discoveries could come from a classroom, a coffee shop, or your couch. The best part, every flagged lens becomes a stepping stone for deeper research. When professionals follow up on volunteer finds with spectrographs or radio telescopes, they're often mapping dark matter, testing general relativity, or chasing after the universe's oldest light. That means your click could lead to a paper in Nature or rewrite a chapter in a textbook. So next time you're scrolling mindlessly, why not scroll with purpose? The cosmos is hiding in plain sight, and it's waiting for you to connect the dots. The next leap in gravitational lensing won't come from just bigger telescopes, it'll come from sharper eyes. Imagine trying to read a street sign through frosted glass, and then suddenly swapping it for a microscope. That's the promise of next-generation observatories like the Extremely Large Telescope, or ELT, now rising from Chile's Atacama Desert. With a mirror spanning 39 meters wider than a blue whale is long, this behemoth won't just see lensed galaxies, it'll dissect them. Where Hubble and James Webb show us smudged arcs and stretched starlight, the ELT's unprecedented resolution could reveal individual star clusters within those distant, warped galaxies, pinpricks of light twisted by spacetime but sharp enough to study like never before. But resolution is only half the story. The ELT's colossal light-gathering power means it can spot lensed objects so faint they're currently just theoretical. Picture a galaxy so remote its light has traveled nearly the entire age of the universe, magnified by a foreground cluster, but still too dim for today's telescopes to analyze. The ELT won't just detect such objects, its spectrographs will unpack their chemistry, measuring the abundance of elements forged in stars that died before our solar system even formed. It's like turning a cosmic magnifying glass into a time-traveling laboratory. And then there's dark matter. Current lensing maps reveal where dark matter clumps, but the ELT could expose how it behaves on scales smaller than a galaxy. Some theories suggest dark matter might be clumpier than models predict, with tiny, dense pockets hiding between stars. By studying how lensed images flicker as stars in the foreground galaxy pass by, an effect called pixel-level microlensing, the ELT could weigh these invisible specks directly. It's the difference between seeing a shadow and catching its fingerprints, but the ELT isn't alone. Coming online around the same time, the Giant Magellan Telescope and the 30-meter telescope will form a network of next-generation observatories, each tackling lensing's biggest mysteries from different angles. The GMT's uniquely designed mirrors will minimize atmospheric distortion, making it ideal for studying the faintest lensed arcs at the universe's edge. Meanwhile, the TMT's adaptive optics, a system that corrects for Earth's turbulent atmosphere in real time, could let it spot planets orbiting stars in lensed galaxies, a feat currently in the realm of science fiction. What makes this era so transformative isn't just raw power, it's synergy. These telescopes will work alongside gravitational wave detectors, dark energy surveys, and AI-powered sky scans, turning lensing from a niche tool into a cornerstone of cosmic discovery. Future observations might combine ELT close-ups of lensed galaxies with Euclid's wide-field maps of dark matter, or pair TMT's planetary detections with JWST infrared eyes. Together, they'll test whether dark matter is cold, warm, or something stranger, and whether Einstein's gravity holds true in the universe's most extreme corners. The most thrilling possibilities lie in the unexpected. With resolution this sharp, astronomers could stumble upon lensed objects that defy categorization, primordial black holes caught in the act of merging, or galaxies so ancient they challenge our timelines of cosmic dawn. Every new lens the ELT uncovers will be a window not just into space, but into the laws that govern reality itself. And as these telescopes push closer to first light, one thing becomes clear: we're not just building better observatories. We're building a new lens through which to see the universe. Gravity is supposed to play by Einstein's rules, but sometimes the universe cheats. Take El Gordo, the fat one, a galaxy cluster so massive and so ancient it defies everything we thought we knew about cosmic growth. Officially catalogued as ACDCLJ 0102-4915, this colossal structure weighs in at a staggering 3 million billion suns, with galaxies whipping around its core at thousands of kilometers per second. By all accounts, it shouldn't exist. According to our best models, clusters this size need nearly 14 billion years to form, yet El Gordo appears fully assembled when the universe was just half its current age. It's like finding a skyscraper in the middle of the Stone Age. Gravitational lensing revealed the true scale of this cosmic rebel. When astronomers first observed its warped arcs, background galaxies stretched into fiery smears by El Gordo's gravity, they assumed standard physics could explain its mass. But the numbers didn't add up. Lensing measurements showed the cluster's dark matter was oddly concentrated in two distinct clumps, as if two smaller clusters had collided at impossible speeds. Simulations suggested such a crash should have torn them apart, yet here they were, fused into a single titan. The only explanation: either dark matter interacts in ways we've never seen, or our timeline for cosmic structure formation is wildly off. El Gordo isn't alone in breaking the rules. The missing arcs problem haunts lensing surveys, massive clusters that should warp background galaxies into vivid curves but don't. One such cluster, IGJ 1426+3508, holds 6 times the mass of the Milky Way yet produces bafflingly faint lensing effects. Some theorists speculate these anomalies hint at self-interacting dark matter particles that bump off each other like billiard balls, smoothing out the dense clumps lensing relies on. Others propose more radical ideas: that gravity itself behaves differently on cosmic scales, or that dark energy's repulsive force kicked in earlier than we thought, turbocharging cluster growth. Then there's the case of the cold spot, a mysterious void in space where lensing patterns suggest far less matter than expected. Normally, such regions should be filled with faint, stretched galaxies, cosmic backlighting revealing the void's edges. But when astronomers trained radio telescopes on it, they found nothing. No hidden dark matter, no exotic physics, just an eerie absence. Some argue it's evidence of a collision with another universe, others think it's a statistical fluke. But lensing doesn't lie. The light bending through that void tells us something fundamental is missing from our maps. These anomalies aren't just academic curiosities, they're cracks in the foundation of modern cosmology. Every time lensing exposes a mismatch between prediction and observation, it forces us to ask, are we missing a piece of the puzzle, or is the puzzle itself wrong? The answer might lie in upcoming projects like the Legacy Survey of Space and Time, which will scan millions of lensing events for statistical oddities. Or perhaps the James Webb Space Telescope will spot more impossible clusters, rewriting the rules of cosmic evolution. What's certain is this: gravitational lensing doesn't just show us the universe's hidden structures. It shows us where our understanding ends and where the next great discovery begins. Could gravitational lensing be our first glimpse into a multiverse? While the idea sounds ripped from science fiction, some physicists argue subtle anomalies in lensing patterns might hold clues to realities beyond our own. Take the cold spot, a vast, mysteriously empty region in the cosmic microwave background where lensing distortions vanish against all predictions. Most explanations fall short, but one radical theory suggests this void could be a bruise left by a collision with another bubble universe in the cosmos's infancy. Like two soap bubbles brushing in a sink, these universes might have nudged each other, leaving imprints in spacetime that lensing now exposes. The math gets wilder. If alternate universes exist, each with different physical constants, their gravity could subtly warp spacetime in ways ours can't. Simulations show such universes might create gravitational echoes, a phantom lensing signals where no visible mass exists. In 2021, researchers scanning the Planck satellite's data found peculiar lensing distortions around the cold spot that matched these very models. The statistics were shaky, but the implication was staggering. What if we're seeing the gravitational shadow of another universe's mass bleeding into ours? Not everyone's convinced. Critics argue these anomalies could stem from instrumental noise or quirks in cosmic inflation. Yet lensing keeps poking holes in conventional wisdom. Another puzzle lies in the Hubble tension, the discrepancy in the universe's expansion rate. Some theorists propose the answer might not lie in our universe at all, but in neighboring ones tugging at spacetime like invisible magnets, their gravity subtly altering how lensed light reaches us. Future telescopes like the Simons Observatory aim to test this by mapping lensing patterns in the cosmic microwave background with pixel-perfect precision, hunting for telltale ripples that betray outside influence. Even if the multiverse remains unproven, lensing's role as a cosmic detective is undeniable. Whether revealing hidden dimensions or simply exposing flaws in our theories, every warped galaxy, every anomalous arc, is a reminder that the universe or universes still holds cards we've yet to see. And as lensing techniques grow sharper, we might not just be mapping the invisible, we could be peering through the cracks of reality itself. Want to see gravitational lensing with your own eyes? You don't need a space telescope, just a wine glass from your kitchen cabinet. Here's how to turn your dinner table into a cosmic laboratory. Fill the glass with water and place it on a white surface near a bright lamp. Now look through the curved side of the glass at a distant light source, maybe a phone screen with text or a patterned wallpaper. See how the image behind the glass stretches and warps. That's your personal demonstration of spacetime curvature in action. The water in the glass acts like a massive galaxy cluster, bending light that passes through it. When background light hits the curved surface, it refracts, changing speed and direction, just like starlight bending around a cosmic heavyweight. Tilt the glass slightly, and you might even create multiple images of the same light source, mimicking how lensed galaxies appear as identical twins or triplicates in telescope images. The circular distortions you see around the edges, those are your homemade version of Einstein Rings, nature's perfect alignment of source, lens, and observer. For an even simpler experiment, try this. Next time you're outside after rain, find a water droplet clinging to a leaf or window. Peer through it at distant streetlights or car headlights. The droplet's spherical shape will stretch those points of light into delicate arcs, miniature versions of the luminous smears Hubble sees when galaxy clusters warp background starlight. Notice how the droplet magnifies some features while distorting others. That's the same trade-off astronomers face when interpreting lensed galaxies. The magnification reveals hidden details, but the distortion complicates measurements. What's fascinating is how these simple tools mirror the real challenges of cosmic lensing. Just as your wine glass introduces chromatic aberration, color fringing around edges, real gravitational lenses create subtle optical artifacts that scientists must account for. And like adjusting the glass's position changes the distortion pattern, astronomers analyze how lensed images vary with different alignment angles to reconstruct the invisible mass distribution. These experiments do more than demonstrate physics, they reveal why lensing is such a powerful tool. Just as your makeshift lens lets you see details in background objects that would normally be too small to resolve, cosmic gravitational lenses magnify distant galaxies beyond our telescope's natural limits. Next time you raise a glass, remember, you're holding more than a drink. You're holding a model of the universe's most elegant natural telescope. The Fermi paradox asks a haunting question. If the universe is so vast and ancient, where is everybody? With billions of galaxies, each hosting billions of stars and planets, the silence seems deafening. But gravitational lensing might hold a key to breaking that silence, not by listening for alien radio signals, but by magnifying the light of distant worlds to hunt for the faintest traces of civilizations we've never seen. Imagine a planet orbiting a star halfway across the galaxy. Normally, its light would be a speck lost in the glare of its sun. But if a massive object, a black hole, neutron star, or even another star, passes between that planet and us, its gravity could briefly amplify the planet's light thousands of times. Suddenly, features invisible to our telescopes snap into focus. Atmospheric chemicals, city lights, even vast megastructures like Dyson spheres, hypothetical energy, harvesting constructs advanced civilizations might build around their stars. Lensing turns these theoretical possibilities into tangible targets. This isn't just speculation. In 2020, astronomers used microlensing to detect an Earth-mass planet floating freely in interstellar space, a rogue world with no sun to warm it. If life can cling to such a nomad, what might thrive on planets orbiting stable stars? Future telescopes like the Nancy Grace Roman Space Telescope could spot lensed exoplanets in the habitable zones of distant suns, analyzing their atmospheres for biosignatures like oxygen or methane. But the real jackpot would be technosignatures, artificial chemicals, industrial pollutants, or the unnatural heat signatures of vast alien megaprojects. The challenge: timing. Lensing events are fleeting, lasting weeks or months at most. To catch a civilization's footprint, we'd need constant monitoring of millions of stars, a task projects like the Vera Rubin Observatory's legacy survey of space and time are built for. Pair that with AI sifting through data for anomalies, and we might stumble on a lensed exoplanet with atmospheric gases that don't belong, or a star whose light curve hints at artificial structures. Some theorists suggest we've already seen hints. In 2015, the star KIC 8462852, nicknamed Tabby's star, dimmed erratically with drops in brightness up to 22%. One wild explanation: a partially built Dyson sphere, its swarms of energy collectors drifting into view. While dust clouds are a likelier culprit, lensing could help resolve such mysteries by magnifying similar stars, revealing whether their dimming patterns match natural debris or something more structured. And here's the twist: if advanced civilizations know about lensing, they might use it too. A sufficiently advanced alien society could position artificial lens stations near massive objects, creating controlled magnifying effects to study distant galaxies or even signal other civilizations. The same phenomenon letting us peer deeper into space might be someone else's interstellar telescope. The Fermi paradox assumes we'd hear aliens if they existed. But what if we've been looking wrong all along? Lensing shifts the search from listening to seeing, offering a way to spot not just life, but intelligence, written in the warped light of 1,000 distant suns. The great silence might not be silence at all. We just needed the universe's own magnifying glass to read it. Imagine a future where we don't just passively observe distant exoplanets through nature's gravitational lenses, we create our own. Picture a fleet of spacecraft positioning black holes or neutron stars between Earth and alien star systems, bending light precisely to bring their planets into razor-sharp focus. The scientific payoff would be staggering: detailed maps of alien continents, atmospheric analysis revealing biosignatures, even the hypothetical glow of city lights or industrial activity. But here's the unsettling twist: if we can do this to them, they could do it to us. The same technology that unlocks the universe's secrets might turn every civilization into a fishbowl, observable by anyone with the right gravitational tools. This isn't just speculative sci-fi. The groundwork is already being laid. Breakthrough Starshot, a project aiming to send tiny probes to Alpha Centauri, relies on precisely directed lasers, a precursor to manipulating light on cosmic scales. Scaling this up to artificial lensing would require harnessing extreme gravity, perhaps by compressing matter into miniature black holes or stabilizing neutron stars as lenses. The physics is daunting but not impossible, and the ethical dilemma is immediate. Does the pursuit of knowledge justify the loss of cosmic privacy? Consider the scientific windfall. Artificial lensing could answer humanity's oldest questions. Are we alone? How common is life? By magnifying an exoplanet's surface, we might spot continents, weather patterns, or even signs of technology like the spectral fingerprints of artificial chemicals or the heat signatures of megacities. For astrobiologists, this would be the holy grail, but for ethicists, it's a minefield. If we detect a civilization, do we announce ourselves, potentially exposing them to existential risks from more advanced neighbors? Or stay silent, hoarding knowledge they might never access? The privacy paradox cuts deeper. If advanced civilizations universally avoid broadcasting their existence, a potential solution to the Fermi paradox, then actively lensing others, might be the galactic equivalent of shining a spotlight into a darkened room. The very act of looking could endanger what we find. Historical parallels on Earth are sobering. Colonial exploration often led to exploitation, and even well-intentioned contact has devastated isolated cultures. Would interstellar observation repeat these mistakes on a cosmic scale? Yet refusing to develop this technology carries its own risks. If another civilization is already lensing us, our hesitation could leave us defenseless, unaware of impending contact or threats. Some argue that survival in a competitive universe demands vigilance. If we don't look, someone else might, and not with benign intent. The dilemma echoes nuclear ethics. Does developing a tool for defense justify its existence, even if it escalates universal tensions? Perhaps the middle path lies in self-imposed limits, like a cosmic version of medical ethics, do no harm principle. We might agree to lens only uninhabited systems, or develop detection protocols that minimize interference, say, by using passive lensing that doesn't require sending probes into alien gravity wells. International treaties could emerge, akin to the Outer Space Treaty of 1967, banning the weaponization of lensing or intrusive observation of inhabited worlds. But enforcement is a fantasy. In a universe vast enough to hide countless civilizations, cheating would be effortless. The only true safeguard might be cosmic humility, recognizing that some knowledge comes with too steep a price. Or perhaps the answer lies in embracing transparency, building a universe where all civilizations openly share data, turning lensing into a tool for mutual understanding rather than covert surveillance. The choice reflects who we are as a species. Do we prioritize curiosity at any cost, or champion a new ethic for cosmic citizenship? Gravitational lensing doesn't just bend light, it bends morality, forcing us to weigh discovery against dignity on a scale as infinite as space itself. Imagine slipping on a VR headset and suddenly floating face to face with a galaxy cluster so massive it warps spacetime around you. This isn't just a far-off dream. Researchers and developers are already building immersive virtual reality experiences that let you step inside the mind-bending world of gravitational lensing. Picture this: with a flick of your wrist, you zoom toward Abel 1689, watching as distant galaxies stretch into luminous arcs around its dark matter halo. Tilt your head and the entire scene shifts, revealing multiple mirrored images of the same quasar flickering like cosmic déjà vu. This is science education reimagined, where the universe's most abstract concepts become something you don't just learn but feel. The magic lies in the data. Projects like the Hubble Frontier Fields and JWST Deep Sky Surveys have given us ultra-high-resolution maps of lensing clusters enough to reconstruct them in 3D down to individual galaxies. Now, teams like those at NASA, a jet propulsion laboratory, are transforming those datasets into navigable VR environments. Using real gravitational lensing equations, every warped galaxy, every stretched arc, reacts to your movements with physics-accurate precision. Want to grab a background galaxy and shift its position? Watch as the lensed images distort in real time, demonstrating how alignment dictates the cosmic mirage. It's like holding spacetime in your hands, but the real breakthrough isn't just visualization, it's interaction. In some demos, users can paint dark matter onto a cluster, instantly seeing how their additions warp the light passing through. Others let you rewind cosmic time, watching lensed galaxies morph as the universe expands or as the foreground cluster's gravity shifts. There's even a prototype that simulates microlensing. Fly close to a virtual star, and rogue planets drifting through the galactic dark briefly flare into view, their gravity acting as cosmic magnifying glasses. These aren't canned animations, they're dynamic simulations where every variable tweak reveals new layers of astrophysics. Educational potential aside, VR lensing could revolutionize public outreach. Picture planetariums where visitors don headsets and collectively explore the warped universe, spotting lensed supernova or hunting for Einstein rings hidden in the digital cosmos. Or imagine classrooms where students manipulate virtual black holes, feeling literally, through haptic feedback, how their gravity bends light at different distances. Already, institutions like the European Space Agency have partnered with VR studios to create lensing modules for schools, complete with guided tours narrated by astrophysicists. The goal isn't just to show lensing, but to make users intuit it, turning abstract math into visceral experience. Yet the most tantalizing applications lie ahead. Future updates could integrate AI, letting users ask the simulation questions: why does this arc look broken? Or what's the mass of this cluster? And getting real-time explanations overlaid on their view. Others might layer in augmented reality, projecting lensed constellations onto the night sky through AR glasses. And as quantum computing advances, we could simulate entire synthetic universes with adjustable physics, testing how lensing would behave if dark energy were stronger or if gravity worked differently. What makes these VR experiences profound isn't just their tech. It's their ability to collapse the distance between human and cosmic scales. One moment, you're marveling at a galaxy cluster millions of light years wide. The next, you're threading through its dark matter tendrils like a neutrino, watching individual stars amplify and fade. It's a reminder that the universe's grandest phenomena aren't just out there, they're patterns waiting to be explored if we're bold enough to step inside them. Gravitational lensing bends light, but can it bend time? The idea of using cosmic magnifying glasses as time machines has fueled countless sci-fi plots, from slingshotting around black holes to peering into parallel universes. Yet reality, as always, is more nuanced and, in some ways, even more astonishing. While lensing doesn't let us hop backward or forward through time like a Hollywood protagonist, it does something arguably more profound. It gives us a direct line of sight into the universe's distant past, no DeLorean required. Here's how it works. Every time you look at a lensed galaxy, you're not just seeing light bent by gravity, you're catching photons that have traveled billions of years to reach us. Take the galaxy cluster MAX 0647, which acts as a gravitational lens for a galaxy so far away its light set out when the universe was just a quarter of its current age. The cluster's gravity doesn't just magnify that galaxy, it preserves its light like a cosmic time capsule, showing us how galaxies looked and behaved in their infancy. It's not time travel, it's light travel, with space-time itself acting as the delivery system. So why can't we use lensing to visit those eras? The confusion often stems from mixing two Einsteinian concepts: gravitational time dilation and lensing. Near massive objects like black holes, time does slow relative to the rest of the universe, an effect verified by atomic clocks on GPS satellites. But lensing doesn't manipulate time, it manipulates light's path. Imagine shouting across a canyon and hearing your echo seconds later. The sound hasn't traveled back in time, it's taken a detour. Similarly, lensed light might loop around a galaxy cluster, arriving later than light that came straight to us, but it's still moving inexorably forward. That said, lensing does offer a form of time multiplexing. When a distant supernova is lensed, we might see multiple images of the same explosion appearing weeks or years apart as light takes different routes around the lens. In 2015, astronomers witnessed this with supernova Revolutionize, which appeared in 4 distinct spots around a galaxy cluster, and then, as predicted, reappeared in a 5th location a full year later. It was like getting a replay button on a cosmic catastrophe, though each replay showed the event at the same stage, just delayed. The real magic lies in what these delays reveal. By measuring time gaps between lensed images, scientists can calculate the universe's expansion rate with precision, testing whether dark energy's push has changed over eons. It's a bit like dating tree rings. Each delayed photon carries a timestamp from its era, letting us piece together cosmic history. Future telescopes might even spot lensed gravitational waves, their staggered arrivals acting as stopwatches for spacetime stretching. So while you won't be booking a lensing-powered trip to the Jurassic period anytime soon, remember, every warped galaxy in a telescope snapshot is a postcard from the past, stamped and sent by gravity itself. The universe doesn't need time travel to share its secrets, it just needs us to pay attention to the light already on its way. Gravitational lensing doesn't just bend light, it bends our entire understanding of the cosmos. From revealing galaxies hidden in plain sight to mapping the invisible threads of dark matter, this phenomenon has turned space-time itself into a lens, offering us glimpses of the universe we once thought impossible. Think about it, every warped galaxy, every stretched arc of starlight, is a testament to the fact that reality is far stranger, far grander than our eyes alone could ever perceive. We've used lensing to weigh black holes, spot rogue planets drifting in the void, and even catch supernova exploding multiple times in the same image. But what's truly extraordinary isn't just what we've discovered, it's how much more remains waiting in the shadows. The next decade promises to push these revelations even further. With telescopes like the Vera Rubin Observatory scanning the sky nightly, and the Nancy Grace Roman Space Telescope set to launch, we're on the verge of finding thousands more lensed objects, some of which could rewrite the rules of physics. Imagine uncovering a galaxy so ancient it defies our cosmic timeline, or a black hole so massive it challenges Einstein's equations, or perhaps the ultimate surprise, technosignatures from a distant world, magnified just enough for us to detect the faint fingerprint of another civilization. The universe is a master of hiding its secrets, but gravitational lensing is our cheat code, peeling back layer after layer of the invisible. And yet, for all we've learned, the most thrilling question remains: what else is out there? Could lensing reveal dimensions beyond our own, or echoes of a multiverse? Might it help us finally unravel the true nature of dark matter, or catch a glimpse of the universe's very first stars? The beauty of science is that every answer spawns new mysteries, and every discovery opens doors we didn't even know existed. So here's your invitation: stay curious. The universe is far from done surprising us, and the next breakthrough could be just one observation away. If you're as fascinated by these cosmic wonders as we are, hit subscribe and join us as we keep exploring the invisible, the impossible, and the utterly mind-bending. After all, the greatest discoveries start with a simple question: what if?